Key issues to take into consideration when differentiating are explained to the tune of an average student. So the purpose of this presentation is to look at the revision of differentiation, but the most important thing, I want to explain the key issues which you are supposed to take into account when you are differentiating. And I'm doing this, guys, to the tune of an average and the below students. So those guys who are very fast, please, pardon me, I will have to get some of these students on board also, altogether. So don't be bored by that. Is it clear? Okay. Differentiate. I hope I'm going to be able to finish, but if I don't finish, we're going to sort it out tomorrow. It's not a problem. Right. Differentiating. Let's get here. What do we normally differentiate? Do you differentiate numbers? Do you differentiate cows? What do you differentiate? No, you don't know. Okay. We normally differentiate functions. Functions. I'm not going to be able now to engage the issue of what are functions and all those things. Maybe I can just give you an example of a function which you've worked with. Then if later you don't understand what the real function is, you can ask, then we can engage that later. Now, assumption is everybody understands what is a function. Right. When we're talking about a function, I think we need to know what we call independent variable. Like, for example, a way of putting example of a function, we can write a function as y equals to f of x. And then there we've got two variables, x and the y. And then x is independent, the x is independent, and the y is dependent. I'm still going to explain this thing further. So we need to understand what we mean by dependent variable, the argument of a function, and somehow I'm putting this in brackets here. Listen, normally when I put things in inverted commas like this, it's something which I'm not really, you know, sometimes you get a meaning of something, but you don't really know how to express it altogether. So I'm talking about a leading function. Some people will say, what is a leading function now? We'll see that I'll make you understand it anyway, even if I'm not able to explain it fully. What do I mean exactly now? I'll make you understand it. A leading function in the context of composite functions. What are composite functions? Remember before we said, if we've got a set here, x, and you say we've got a set here, y, a set y, and a set here, z. You can define a function here, which gives you values of f of x there. Then maybe define another function there, which, let's say this function is g. Then this function here gives you the values of f of g of f of x. Then you've got this function which comes straight there. Then you would come and say this is h, and this h is the composite function of that. Altogether. So then that's where I'm talking about the leading function. Because now what happens now? As it is here, this f of x here is the argument. First thing they must understand now what I'm talking about when I'm talking about the argument. The argument, I talk about argument here. F of x here, as it is here, is the argument of g. But when I'm looking at f of x here, x is the argument of f. Altogether. So when I'm saying now writing a y is equals to g of f of x, I can now say this is the leading function. You understand what I'm saying? Yeah. There's no I can explain that thing unless I show you what I'm saying. First of all, this function, let's say this function was x squared. And this function here was sine of x. As a function written y equal to sine of x. So what will happen here? H will be equal to sine of x squared. There are two functions involved here, x squared and the sine squared. But now this is sine of x squared. Then I call sine a leading function. Altogether. You might never have ever heard this thing from somebody else, but this is me. And this is how I talk, this is how I communicate the things. Altogether. As long as I can get the message across clearly. Is it clear what I'm talking about? Okay. Then, the next thing is the following. This is exactly what I'm saying. This f here, we've already identified is as argument. And I've explained it there. This argument can be any other function. And the f here is a function. But f here is the function. It could be sine, it could be cos, it could be anything. That's the function. And then y, in this case, we're saying y is the function of x. That's how we can read that. Y is a function of x. But when we write this thing exactly as we've written here, as y is a function of x, we simply mean that this function can be represented as a graph on a system of coordinate, xy coordinate, xy coordinate. This is the system of xy system of coordinates. That is the meaning of this. When I'm writing something like this, I'm just simply meaning that this function can be represented on a system xy coordinate. What if I write y is equals to s of t? Now my independent variable is t, my dependent variable is y, and that function I call it s, which means now I've got a system of coordinates here which I can write as t, and here instead of using y, I can even use the x of t, meaning here I get the independent variable. Along this one, I get the values of the function. Then somewhere there, I will get a kind of a curve which describes that function. All together, guys? That's what I'm talking about. Any questions? So this is just a symbol which I'm asking you to decode now. I'm trying to make you decode this. When I see this thing, how do I read it? How do I understand it, what it means? Is it clear to everybody? Okay. So then, let's go. So then that's the thing. The argument, I put there the argument brackets function. When I've got this function symbolized this way, what can sit here as the argument can be actually another function. I've already shown it. I said there, if I've got a y equals to x squared, and I've got another function y equals to sine x. The two things here are saying exactly the same thing. This is a function of x. So this can be plotted on an xy system of coordinates. This is a function of x. So this can be plotted on a similar function of coordinates. All together. So then if I have it like this, we must understand that what can sit here as an argument can also be another function. Then when we do that, then we've got this composite function, which is h of x, and this is sine of what? Of x squared. Is that making sense, guys? So that's how you must read that. Any question? And again there, the question of leading function, I think you can see it there, x is leading. But I can change this thing around. I can actually change this thing around, and the k of x, which is, I want now the parabola to act first, to act next after the sign. So I'll have here sine x all squared all together. So in that chain of x, y, z, x, y, z, in that queue, which means what comes here first is sine, and what comes there is x squared. So if I compose that, then I get this one. As you can see, these two functions are different. If I remove these brackets, I will write this thing as sine squared x. And this one is that. They are two different things. You must understand that. All together. Okay. Then, already when I'm talking about these things, and considering this to be revision of differentiation, I expect you guys, all of you, to be now fluent in the following. What I call here standard derivative. For example, what do I mean by standard derivative? I mean that if I got sine like this, you must be able to answer immediately what is the derivative of sine x with respect to x. There, when I'm writing that, I'm saying derivative of sine x with respect to x. That's you can read it. And then I can abbreviate, if I consider that sine is y, I can simply denote that as dy, d what? dx. Then, if you can answer this question here, then I can say you know what are standard derivatives. What is the derivative then? Come again? Cos sine x. That one I'm expecting you to know. But if you don't know, guys, there's nothing wrong with you. Please try to go and sit down and revise these things because you have seen them before. All together. Now, what I'm going to do in this presentation, I want to develop an exercise here which involves these things, in such a way that at the end of this presentation, you must understand exactly the gist of what is it to differentiate a function, the process, so that you never differentiate later by accident. Are we together? So now if we have got these ones, look at this one, look at this one, this one. If I consider this to be 0 and that to be 0 and that to be 0 and all these coefficients to be 0, then there I've got y is equals to an x to the power n. And then when I say dy dx, you must be able to answer me this one. Who wants to tell me this one? Okay, I'll remind you. People are afraid to make mistake, but never be afraid to make mistake. The answer to this one will be something like this. N, this very n. X, n, the same n, minus 1. Then we come up here, we'll have this thing as n times an x to the power n minus 1. In such a case that if this was x to the power 2, then this y prime, this is another notation for dy dx, which I'm reminding you also, dy dx, this will simply be 2x2 minus 1 equals to 2x. Why am I doing this? I'm showing my working. I'm showing, even if it's a grade 1 child, you will see how did this transform from here to there. You will see that I subtracted 1 there because a grade 1 child knows how to subtract. All together. So what I'm saying there, what I want to remind you, it's important to show essential steps of your work. Don't omit essential steps of your work, then you lose marks, then you complain. Please. Are we there? Okay. Are we fine with that? Then including this must be known. How do you differentiate this? This must be known. How do you differentiate that? That's not what I'm emphasizing on now. I'm emphasizing on something else, which I'm going to explain. Now, let's go on. Now, what am I saying here? We now want to, with an example, recap the essential of the process of differentiation. That's what was said in that first sentence which I was struggling with there at the beginning. That I want to explain the essential, what is supposed to be done when you are differentiating, to avoid differentiating by accident. Then what I'm going to do is, we take this example, we call sign there the leading function like we've agreed, we're going to call it leading function. A word is used to just communicate something. So leading, you might understand the leader to be a person leading something, but here I'm using it different. You must understand in this context, how am I using it as a component. So that leading function is what is that. And our parabola here, x squared, is the argument. But as an argument, you must see that it is a function. So if it is a function, it must have its own maybe derivative, like the one we've just seen before. So we've got these two functions there. So in this case, these two functions, what we know about these two functions, that's our point of departure. In this case, what we know about this function, we know them, we know their graphs, we know their derivatives. That's our point of departure. Is it clear, guys? Okay, so where are we getting to? We're getting here. We know that the derivative of that, we've already worked it out, is that and simplified it. And we know the derivative of that is cos that. But we know from the beginning when we calculated differentiation, we used this kind of a limit. I'm going to use it again here so that by the time we get to the results, I can interpret the results to you. Then you can go out of this room with a kind of a sitting process, squarely sitting in your system. How do we differentiate? In such a way, tomorrow when I ask you, how do you differentiate the function? You can tell me that we differentiate the function by doing 1, 2, and the 3, or the 4, depending on how many steps are involved. Are we together? Okay. So how do we use this quotient to differentiate this function? First of all, maybe let me explain this thing. First of all, if you've got a function like that, I think you remember that, a curve like that, and I've got a point there, and if I want to get the derivative, the derivative of this function at this point, I'll actually do it by kind of a way of approximating it bit by bit. step by step. What can I do? I can start by drawing a line here, which cuts those 2 points there, and that we call a second line. And then there, I hope you understand that when I've got this point here, this point has got coordinates x, the first coordinate. The second coordinate is f at x, which is y. Out together. And when I got this point here, if I call this point x, I move this distance up to there, a point which is directly below there. Then this point here, I'll call it x plus delta x. How do I read this thing? I read it as change in x. The letter is delta, this is x, but I read this as change in x. What is change in x? This movement here, from here to there. So this number which is here is standing as x plus this change, in other words, an increase in x in this case, and that. So the point here will be an x plus change in x, comma, f of x plus change in x, that brackets, that's the point. So remember, derivative also is going to do with what we call rate of change. So if I were to talk about the rate of change of the function between these 2 points, I need to have this value, which is f of x. I need to have that value, which is f of x. So now if I want to look at it, if I change the value of x by so much, how much does the function value change? I will end up with this kind of, without the limit, I'll end up with this kind of a quotient. Without the limit in this initially. But then what will that give me? Only from here, guys, listen, from here to there, I'm looking at those 2 points. That thing is giving me the average slope between these 2 points. The average slope. When I'm saying average slope, is the slope which I'm considering between these 2 points. It's not the slope at this point, it's not the slope at that point, it's just an average slope between these 2 points. And that does not say necessarily anything about particular points. It's just an average. Are we together, guys? So now if I want to approximate the slope here, what will I do? I will maybe decrease the change in x to somewhere there. And then draw another line there. If I keep on doing that coming here, you'll see that at the end, the line I'm going to have here is going to be a line like outside the curve total. Because why? This point here is coming closer and closer to this, and this line comes out there, and that line there is what we call the tangent line. So when I calculate this limit, actually, I'll be approximating the slope of this tangent line. Are we together? And then when I get the slope of this tangent line, and a line has got a constant slope, so it's the slope of the tangent line, but the tangent shares this point with the curve. I'm saying the tangent shares this point with the curve, and the tangent has got a slope. Then I call the slope of the tangent the slope of the curve at that point. Then I call the slope of the curve at that point the derivative of the function at that point. Am I making myself clear? Sorry, you didn't understand. The tangent has got a slope. Yes or no? The tangent has got only one point sharing it with the curve. Is that right? Then the slope of the tangent, I'll call it the slope of the curve at that same point. Why the slope of the curve at the point? Because the curve there has got a different slope as compared from there to there. It's got a different slope as compared to there. All together. So in simple, tell yourself, a curve takes its slope from its tangent line. Sorry, the slope of a curve at a point is inherited from the slope of the tangent line at the same point. Am I making myself clear? Yes or no? Then what happens now? Here is a curve, is a tangent. A tangent shares a point with the curve. A tangent has got a slope. Then the curve takes its slope from the tangent line. Am I making myself clear, guys? Okay, good. So then there, when we get that limit there, we'll call that limit the derivative of the function there. But if this point x is just a general point, what do I mean by general point? I can choose a particular point as x is equal to 2. I do this, I'll get a slope at x is equal to 2. If I choose x equals to half, I do this, I'll get a slope at when x is equal to half. But if I choose just x, when I choose x, just x, and I don't assign a particular value to x, then I'll call that a generic point. Now it's a general point. If I do that and I do this, I'm going to get a function here. A function. I said a function. And that function is what I'm going to call f prime of x. And that function is what I'm going to call the derivative of the function. So if this function was x squared, for example, let's just say if this function was x squared, and I do this, and I do this, I'm expecting here to get 2x altogether. But now, at the moment, I'm not explaining how to get that 2x. But now, what I'm going to do here now is going to reveal to you how to get this kind of a thing. Can we start doing that now? The introduction is fine? Nobody's got a query? Okay, right. Let's start with this function. I recognize that this function is a bit tedious. It can take us a lot of time. It's fine. But let's start it. If we don't finish it, we will finish it tomorrow altogether. So what would you do? We would evaluate this function here. Then if we evaluate this function here, we evaluate this function in a point like this, and keep this word limit here, then which means we're going to have a limit as change in x is going to 0. Then have in the numerator there, we're going to have sine of x plus delta x. But in this case, is sine x squared, which means this is what is squared, minus sine x squared, all divided by. Then the next step, I'll just write limit there, delta x going to 0. We've got x plus delta x all squared equals to x squared plus 2x delta x plus delta x squared. Are we together? Okay. Then when we've done that, I'll try to make this a b and make this an a, and then think about what we'll do when we've got sine a plus b. If I'm not mistaken, sine a plus b is sine a cos b plus sine b cos a. Let's just double check that, but I think that identity is correct. It's correct, huh? Okay, I think that is correct. Okay, so if we do that, which means here, if we now apply sine x plus delta x and apply to that, we're going to have sine x squared cosine 2x delta x plus delta x all squared plus sine 2x delta x plus delta x all squared cosine x squared. Do we agree? All together. But then, yes, that's what we have there. Then this is what we're going to put in the numerator. It was sine x squared cosine what? 2x delta x plus delta x all squared in brackets plus sine 2x delta x plus delta x all squared multiplied by cosine x squared minus sine x squared. Notice that this minus sign is this one, eh? And then delta x. Please guys be patient. Long calculations sometimes make people lose interest. But the most important thing is that when you develop this thing logically, you understand it and you follow it nicely, then when I make a conclusion at the end, it will be a conclusion which sits because you sort of followed. I'm not asking you to understand almost everything that you can do this thing again on your own, but try to understand all the logic I'm following here. All together. Okay. Now, let's do some kind of simple things here. I'll do simple things here, very, very simple. I'll focus on one thing at a time and tell me something. Look, this sign, this delta x is going to 0, and this is going to 0. Actually, the whole argument here is going to 0. But if you remember cosine, close to 0, cosine is close to 1. You understand what I'm saying? Now, if cosine is close to 1, which means this term here, from here to there, is almost close to this one. Do you understand what I'm saying? If then they are almost close, the difference between them is negligible. When I'm saying something is negligible, I simply mean that it's something you can ignore and do without. Altogether. That is only when delta x is going to 0. Altogether. So which means in this case, considering what I'm just saying now, we can simplify this with that. I repeat, I'm saying cosine close to 0 is close to 1. So, which means this thing is, since the argument here is close to 0, this is close to 1. If this is close to 1, this is close to what? 1 times sine squared. But here we've got sine squared. Then this is sine squared, almost 1 sine squared minus sine squared. The difference is very small. I never said it's 0. I'm saying it's negligible, can be ignored. Altogether. So I ignore it. Then what are we left with here? We're left with limit delta x 0. Then what we have here? We've got sine 2x delta x plus delta x all squared multiplied by cosine x squared, and then over delta x. Are we there? Then I'm going to do the same thing of that sine a plus b. Now my a is going to be this part, my b is going to be that part. We do exactly the same thing. So then equals them, then limit as delta x is going to 0. What's going to happen? It's going to be sine 2x delta x cosine delta x squared plus sine delta x squared cosine 2x delta x. All this multiplied by cosine x squared over delta x. Am I making myself clear? Okay. Right. Right. Let's do this. For me, and I want you to share this understanding with you, if delta x is close to 0, delta x squared is even closer to 0. Yes or no? Numbers which are less than 1, when you square them, they become smaller. Take half, square it, it becomes a quarter. Take a quarter, square it, it becomes smaller. Altogether. So delta x is even closer to 0. Then we think of cosine around 0, next to 0. Cosine close to 0 is 0. Altogether. The curve, do you know the curve of cosine? The curve of cosine is like this. 0 there, 0 there, then goes like this. So as you come to 0, whether come from this side or this side, cosine close to 0 is almost 0. So if that is the case, and the cosine close to 0, if this was close to 0, if this delta was close to 0, make this 0, this would be 1. So this becomes 1 times 0. Then this term can be ignored. Why I'm doing it this way, why I'm guiding you there, is because I know where I'm guiding you to. So you mustn't question me, why are you choosing that? It's because I know where we're going to. All together. Okay. So now we've got this 0. What are we left with? We're left with this. Limit delta x going to 0. What is that? This is cosine x squared sine 2x delta x. Let me actually do this thing once now. This cos squared, this delta x squared also, close to 0 is even closer to 0 when it's squared. Then cosine of 0 will be closer to 1. Then there we got 1 times that. Then we can just write that altogether. So then there, this is divided by 2 x. No, sorry. I'm trying to say it divided by delta x. Remember, this is an argument, so there's no simplification you can do there. That is an argument of sine. This is outside that. So now we're left with something like this now. Now let's write this thing nicely now. What can we do here? We can write this as cosine x squared multiplied by the limit of, as delta x is going to 0, of sine 2x delta x over delta x. Then what? I'll remind you of something which you might have forgotten, but don't feel guilty. When I want to conclude this thing, now I want to conclude this thing, but I don't have a way of concluding, but I remember something. What I remember is that the limit of, as x is going to 0, of sine x over x is equal to something. That is called a special limit. What is it equal to? It's a special limit. What is it equal to? You forgot it. It's equal to 1. As long as this argument there is x and x there is x there, this is equal to 1. The limit is equal to 1. You can verify it. I can give you some information to go and check it. It's fine. But that's, understand that to be equal to 1. So now, how do I conclude this? This is how I conclude it. Check how I conclude it. I see here, this is delta x. It's not the same as what is here. It's not the same as what is there. But here, it's only 1 when this argument is sitting there and is sitting there. But there I've got a different thing and different things sitting there, different things sitting there. What do? I can just multiply this by 2x and multiply by 2x. What if I multiply by 1? It's 2x over 2x is 1. Altogether. And then I can multiply this one by 2x. Why don't I care that I multiply by 2x? Because even if I multiply by 2x, as long as my delta x is going to 0, the whole thing is going to approach 0. Because every time I multiply a certain fixed number with a number which is going to 0, that number becoming shrinking towards 0. So when it's looking like this now, it looks like what is sitting here is sitting there, is sitting there, is sitting there, and is sitting there. What do? I need to rewrite this nicely. The only thing now which is the problem is this 2x. What can I do? 2x does not depend on delta x. So the next thing I'm going to write here is going to be cosine x squared multiplied by 2x multiplied by this limit. 2x delta x going to 0. This one is supposed to be limit of what? Of sine 2x delta x over 2x delta x. Then there, I'm happy, I'm going to have something like this. So this limit is equals to 1. And then what do I have here? I've got cosine x squared multiplied by 2x. I'm putting it aside like that so you don't confuse this 2x with the argument of the function. The argument of the function is x squared multiplied by 1. Then let's summarize. We started at y equals to sine x squared. We're landing at y prime equals to cosine x squared multiplied by 2x multiplied by 1. I don't even worry about writing 1 because 1 times a is a. So it multiplies exactly this. But what do we know? We know that the immediate derivative of sine x is cos x. We know that the derivative of we know that the derivative of x squared is what? Is 2x, which is that. Now let's sing this. Let's summarize this. What did you do here? What did you do? We were given sine x squared. To get its derivative, we need to call upon the immediate derivative. I'm saying the immediate derivative of the leading function, which is cos. Retain the argument. In other words, keep the same argument. but multiplied by the derivative of the argument. Is that clear, guys? Is that clear? We're given this function. We're differentiating it. What comes up? Cos the immediate derivative of that function with the same argument, but that immediate derivative multiplied by what? The derivative of the argument. Now, I'm saying now, you must be able to say, when somebody says, what is the process of differentiation? You must say, whenever I'm differentiating, I must get the derivative of the leading function and multiply it by the derivative of the argument. If you can say that accurately as I'm saying it, whenever I'm getting a function, I don't know what is the argument because the argument could be another function. So to differentiate it, I must make sure that I get the derivative of the leading function. In this case, the derivative of sine, the immediate derivative of sine is cos. Simply retain the argument and multiply it by the derivative of the argument. All together? So now, if you know all the immediate derivative, what I call the standard derivatives, you must never overlook this. This is how we differentiate. In this case now, this is what people call chain rule. And for me, chain rule is present from the first day you start differentiating. What is the derivative function? The derivative function is the derivative of the leading function multiplied by the derivative of the argument. But the argument can be a function itself also with its argument, which is a function. What do? You repeat the same thing. What am I talking about? I'm talking about something like this. I'm talking about something like this. Here is function y is equals to e to the power sine of x squared. How many functions are involved there? E exponential, sine, and the parabola. But we know that when we differentiate the exponential function, what does it do? It comes back exactly as it is. So now the derivative here will be, without doing all that limit story, I'm now following this last sentence I said. The exponential function will come back exactly as it is. Same argument, same everything. That's its derivative. But it must be multiplied by the derivative of the argument. In this case, I'm going to say by the derivative of its argument with respect to x. In this case, the argument is sine x squared. What am I doing there? I'm showing my working. The next thing, this will be equal to the same exponential function, sine x squared, multiplied by the derivative of what? Of sine. I'm just saying derivative of sine is cos. As cos, it's going to be cos retaining the same argument multiplied by the derivative of the argument. Are we together, guys? Finally, writing this nicely, I'll write this as 2x cosine x squared multiplied by, maybe not to confuse with the argument, I'll write brackets e sine x squared. And that, guys, is the derivative of that function. Are we together? I think we're going to stop there. Then we'll continue tomorrow. So at this stage, I would like to say thank you for listening. My name is Charles Wasfani Msipa.